Hi guys, welcome back to my YouTube channel. Today I'm going to be doing organic chemistry, the theory which entails basics for naming, naming of organic molecules, right? So with organic chem, we are usually talking about, or we refer to organic molecules, which we say are molecules that contain carbon atoms, right? And then under organic molecules, we say we can be able to represent them in three main ways. So we can be able to represent organic molecules in three main ways. We can use what we call molecular formula. We can also use structural formula. We can also be able to use condensed structural formula, right? So what is the difference between these three? So when we say we're talking about organic molecules, we say they contain carbon atoms, right? Molecular formula, they show the number of carbons and the number of hydrogens, or rather other elements that are there present in that structure, that molecule. So they show how many carbons you have. For example, I can have a molecular formula that says C2H6, right? So it's telling me that in this molecule, there are 2 carbons and 6 hydrogens, right? So if you remember, in the previous grades, then we'd refer to what we called valency, which is how many bonds need to be formed by a specific atom in order for it to be stable, right? So we'd usually speak of carbon having a valency of 4, hydrogen has a valency of 1. So hydrogen can form a maximum of 1 bond, and then carbon needs a maximum of 4 bonds, right? So when we are talking about the structural formula, then it must fit the valency of that specific atom. For instance, I said carbon must always have 4 bonds around it in order for it to be stable, and hydrogen must have 1 bond. So if I was to draw the structural formula for this molecule, it would be 2 carbons, right? And we said how many? 6 hydrogens, right? So this one we call a structural formula, which shows the atoms and the bonds between different atoms in the molecule. We call it a structural formula. We can also have what we call a condensed structural formula. This one doesn't show all the bonds, or it's more like showing how many carbons, or rather how many hydrogens or any other substituents are bonded to each carbon, right? So I can have a condensed structural formula I'm going to use for the same molecule. It will be CH3CH3, right? So it's telling me that the first carbon, or the 1 carbon, has 3 hydrogens, and then the other one also has 3 hydrogens bonded to it. And then also, obviously, between the 2 carbons is going to be a bond to make up the 4 bonds around the carbon atom, right? So this is ways that we use to represent the molecules, organic molecules. So when it comes to the actual organic molecules, we can have what we have hydrocarbons. When it comes to the actual organic molecules, we can have what we call hydrocarbons, right? As the word, if I was to break it down, hydrocarbons, right? So these molecules only contain hydrogen and carbon in their structure. So we can classify them into two main types. We can have what we call saturated and unsaturated hydrocarbons. So the saturated hydrocarbons have no multiple bonds between adjacent carbon atoms. So no multiple bonds between adjacent carbon atoms. And then the unsaturated have multiple bonds, one or more multiple bonds between adjacent carbon atoms. So I'm going to stick to my example again. My example had 2 carbons. So example of a saturated hydrocarbon would be something like this, right? There's only single bonds between the 2 adjacent carbon atoms. If I was to speak of an unsaturated hydrocarbon, then I'd be referring to something like this. I'll get to the naming a bit later, right? So there's now a double bond between the 2 carbon atoms. So this we call unsaturated, this one we call saturated, right? To break it down a bit further, the unsaturated hydrocarbons can be divided into 2, right? So for the saturated, we only refer to what we call alkanes. And then for the unsaturated hydrocarbons, we can have what we call alkenes and alkynes, right? So now this we call homologous series. So the name that is given to a certain type of organic compounds, right? So when we're talking about organic compounds, think of it as a family. If you think of your family and your friend's family, they're different. So for instance, you could have a surname that is for your family lineage. And then your friend also has a surname that is for their family lineage. So usually in different families, there's specific features in their looks that are common in that family. So you find that you end up saying there's a resemblance in that family. Same thing with organic molecules. There can be specific features in an organic compound that tell you to which family or organic or homologous series rather they belong to. So we call those functional groups. Think of functional groups as those special features that each family has that makes them different from another family. But the formal definitions are a homologous series of organic compounds is a series of organic compounds that can be described by the same general formula, right? And then a functional group is a bond, an atom, or group of atoms that determines the physical and chemical properties of a group of organic compounds. So like I said, the functional group is that special feature, and then the homologous series is the name of the family or the surname in our instance, right? So when we refer to hydrocarbons, then we split them into their different families. We say we have saturated, we call them alkanes. So this is homologous series. The name alkanes is a homologous series, right? The name alkene and alkyne is also a homologous series, right? So when you're looking at them, they're each going to have these specific features that are called a functional group that differentiate them from another family. So if we talk about alkanes, their functional group is, let's talk about the functional groups. Let's call this number 1 and call this number 2 and call this one number 3. If we're talking about alkanes, their functional group is going to be the fact that what makes them different is there's going to be single bonds only between adjacent carbon atoms. And then they're also going to have what we call a general formula. The general formula is just telling you that it's like deriving an equation in terms of variables that tells you that generally in that family, when you have a specific number of carbon atoms, you're going to have a specific number of hydrogens, right? So for the alkanes, the general formula is CnH2n plus 2. So it means if I have n number of carbon atoms, I'm going to have 2n hydrogen atoms bonded to the carbon atoms plus 2. So that means, for instance, if I have two carbon atoms, like I did in my example that I showed you, then I'm going to have 2 times 2, which is 4, plus 2, which is equal to 6 in total, hydrogen atoms that are going to be bonded to those carbon atoms. So it means the first molecule that I showed you was actually an alkane, right? And then let's go to the alkenes. So alkenes also have their special feature, their functional group that differentiates them from the others, right? When you look at alkenes, they have a double bond between adjacent carbon atoms. So we can have dienes, but mostly for grade 12 purposes, we deal with one double bond. So it means in their carbon chain, they can have a double bond between 2 carbon atoms. They also have a general formula. Their general formula is CnH2n. So again, for the one that I showed you, it had 2 carbon atoms, and then it had twice the number of hydrogen atoms bonded to that. So I had 2 carbon atoms and I had 4 hydrogen atoms. That's for alkenes, right? And then we can also have alkynes. Functional group, their special feature is they're going to have a triple bond between adjacent carbon atoms. And then their general formula is CnH2n minus 2, right? So if I have 2 carbon atoms with a triple bond between them, then I'm going to have 4 minus 2 hydrogen atoms, if it's just hydrogens, because right now we're just speaking about hydrocarbons. Then I'm going to have 2, which means if I have 2 carbon atoms, I'm going to have 2 hydrogen atoms bonded to them if there is a triple bond, right? And then there's usually when we are naming them, because I said we can be able to represent the molecules using structural, molecular, condensed structural formulae, but we can also be able to describe them using names. When we're naming them, we also have special suffixes at the end of the name to be able to differentiate the different functional groups, right? So I always say it's good for you to know the suffix for each. So the suffix for alkanes is ane. The suffix for alkenes is ene. And the suffix for alkynes is ine. Right? Now going back to what I showed you, which was basic, it had the molecule that I showed you had 2 carbon atoms. If I was to name, there is also a way in which we write down how many carbons. Remember we said organic molecules must have carbons. So there is a way in which we write down how many carbons are in the longest chain of that specific organic molecule, right? So there's some other parental naming that you must know. When we talk about naming, then we refer to the number of carbons in the longest chain. So we call it the parent chain. Right? The parent chain can have 1, 2, 3, 4, 5, 6, 7, 8 carbons. Of course, it can have more, but for grade 12 purposes, we do up to 8, right? So it can have 1, 2, 3, 4, up to 8. When I'm referring to a molecule that has a longest chain with a maximum of 1 carbon, then we use meth, right, to name that parent chain. So for instance, for example, if I have a carbon like this, bonded to hydrogens, like that, then I can have the name. I'm going to have a prefix if I have substituents, and I'm going to have a parent, and then I'm going to have a suffix. Remember the suffixes that I showed you. It was ane for alkanes, it was ene for alkenes, and ine for alkynes, right? So now when I'm naming, I put together the name of the parent chain or the longest chain plus the name that describes the kind of functional group I have in that molecule, right? So if I'm naming the parent, I count how many number of carbons I have in my longest chain. So if I have 1, then we say the parent is meth, the name of the parent chain, and the suffix is ane, right? So we can have what we call, in this instance, the IUPAC name. We call it an IUPAC name. Is going to be methane, right? If I have 2, then we use eth, which means if I now have 1, 2 carbons, then this would be named the parent, suffix. This would be, since it has single bonds only between adjacent carbon atoms, that's ane, and then I have 1, 2, which means the name, IUPAC name, would be ethane, right? I can do this for all basic hydrocarbons that are alkanes, which means they only have hydrogen bonded to the carbon atoms, right? And the single bonds only, they're saturated between adjacent carbon atoms. So when the longest chain has 3 carbons, then we say the parent, we name it with prop. 4 is bute, 5 is pent, 6 is hex, 7 is hept, and then 8 is oct. So I could go on for all the alkanes, which means an alkane with 3 carbons would be named propane. Butane, if it has 4, 5 pentane, 6 hexane, 7 heptane, and 8 octane, right? I could also still use the same parent chain naming for alkenes, alkynes, and all the other types of functional groups that we're going to do, right? So the naming, there's some basic rules that you must remember when doing your IUPAC naming. Number 1, count the number of carbons in the longest chain. And then assign numbers to the carbon or to the carbons. And prioritize the functional group. So remember I said functional group is that those features that make all the organic molecules to be unique, right? It's like those family features I was talking about where I said you end up calling it resemblance because there's something common in different family members or in people who belong to the same family. So I said when you are now numbering, you have to prioritize the functional group over any other substituents, which we're still going to talk about. So you have to prioritize the functional group. And then number to give the lowest number possible to the substituents. Right? So when you are numbering, we're going to speak of different instances. Sometimes we're going to say, in this situation, you must prioritize the alphabetical order. In this situation, you must give the lowest number possible to most of the organic, of the substituents in the organic molecule, right? So it's going to be varying according to the scenario that you have. So you must number to give the lowest number possible to the substituents, right? And then when you write the name, write the substituents in alphabetical order, right? So we're going to speak of different substituents. For instance, when I have some halogens, instead of a specific carbon in an organic molecule, then I'm going to have to give or to name, when I write down the IUPAC name, in an alphabetical order. So I can have maybe a bromine and a chlorine. So the bromine, because it's a B comes before the C, is going to be written first in the IUPAC name. So when you're naming, then when you have substituents, you have to consider the alphabetical order of writing the names as well, right? I said any other important things for naming, I'm going to mention them as we do more examples. So we can have what we call substituents, like you heard I've been saying. So we can have what we call haloalkanes. Let's call this number 4. Haloalkanes. So with haloalkanes, like to think of it of a certain branch of a family. It's like having someone getting married and starting their own family. That family that they're going to start is going to have slightly different features, but they actually still form part of the main family that they were born into. So haloalkanes, we think of them as a separate functional group to simplify things, but they're not really. The only thing is you still have alkanes, but they just have substituents which are going to be halogens. Hence the name halo. The halo is for halogens. Alkanes means there are no double, triple bonds between the carbon atoms, right? So when you have haloalkanes, they also have their own general formula, and they also have their own functional group. So this haloalkane is again the homologous series. Right? And then when you have haloalkanes, the functional group can be represented like this. There's going to be a specific halogen, which we refer to as X. So X refers to halogens like Cl, Br, and fluorine, right? And then can also be iodo, but usually it's the first three. And then we can also have a general formula, which is Cn H2n plus 1 X, right? Again, the X is representing chlorine, bromine, fluorine, or iodine. But when we are naming them, when it comes to haloalkanes, we name a chlorine substituent as a chloro, bromo, fluoro, and iodo, right? So when we're naming them, when we have any substituents, like I said, you have to give the position of the substituent. The same way you have to give the position of a functional group. So you must always give the position of the substituents, right? So let me take a simple example since I've already given you the rules for naming. Let's take something like this. This is obviously a structural formula. And then let's say we have a Cl, and then we have hydrogen, another hydrogen, and another hydrogen here. This is my example. And then the question says, give the IUPAC name of this organic molecule, right? I said the first thing you count how many carbons you have in the longest chain. So in my instance, I'm going to have 1, 2, 3 carbons, right? But I said when you are numbering, you have to prioritize the functional group if there is one. If there are substituents, you also have to give the lowest position possible to the substituents. So I can't number from left to right. I can't make this carbon to be my position 1, 2, 3. I have to give the lowest number to the carbon that has the substituent in this instance. So I'd number this as carbon 1, carbon 2, and carbon 3, right? Then when I'm naming, I prefer to use this prefix, parent, suffix to avoid any mistakes of forgetting any part of the naming, right? I said the prefix is going to be there when you have substituents. So in this instance, I have a substituent. Whenever you are naming a substituent, you have to give its position, because I can have a chlorine in the second position, which means I can have an isomer of this specific organic molecule. So I have to be specific where my chlorine is in this instance. So it's going to be 1 chloro, right? And then the parent has 1, 2, 3 carbon atoms, which means if you go back to my naming of the parent chain, that's going to be prop, right? And then there are no multiple bonds between carbon atoms. There are only single bonds, which means it's an alkane. So it's going to have a suffix of A. Now put everything together to write down my IUPAC name. Put everything together. It means the IUPAC name is going to be 1-chloropropane. Right? The dash we only put in between a number and a letter. The dash we only put in between a number and a letter. This is my example 1. And then I can have another situation where I have a haloalkane, but it has more than one halogen substituent. So when I have that situation, second example like this, my example 2, right? I can have a chlorine here and another chlorine here. And then I can have hydrogens. Right? So when I have a situation like this, then when I am naming, then I also have to assign the positions like I did before, right? Remember I said when you are assigning the positions, you give the lowest position or the lowest number to the substituents if there's no functional group. So if I look at my numbering, if I number from the left, then this is going to be position 1, 2, 3, 4, 5, which means the first carbon is going to be in position 3, or the first chlorine is going to be in position 3, and the second one is going to be in position 4. However, if I number from the right, it's 1, 2, 3, 4, 5, which means if I'm numbering from the right, the lowest number of the substituent is 2, and then the next substituent is going to be in the carbon, the third carbon. So when I compare the two between numbering from the left and numbering from the right, it's best to number from the right, because then I'm going to get to assign the lowest numbers possible to the substituent. So I'm going to number 1, 2, 3, 4, 5, right? And then we have prefix, parent, and suffix, like that. Prefix now has a chlorine in the second carbon and another chlorine bonded to the third carbon. So I have to specify both positions. Even if both the chlorines were on one carbon, I'd say 2, 2 dichloro for my prefix. So I have to mention, even if it's more than one chlorine bonded to one carbon, I have to specify how many chlorines are bonded to that carbon. So if I'm naming this one, the prefix would be, there's a chlorine in position 2, there's another one in position 3, right? And then it's going to be dichloro. Di means there's 2 of them in the compound. And then the parent has 1, 2, 3, 4, 5, which means it's pent. And the suffix has, or the suffix is based on the functional group, single bonds only between adjacent carbon atoms. So that's A. I put it together. Then I'm gonna have 2.3 dichloro-pentane, right? It's just one name, just that I ran out of space, but you would not separate the dichloro and the pentane. You just make it one name. I can also have another situation where I have different substituents or different types of halogens as substituents in one organic molecule. So let's take example 3. Right? Let's make a chloro, and a bromo. Right. When we look at the substituents, there's no one substituent that takes priority over another substituent. The only thing that takes priority is a functional group over any substituents. So when I have substituents only in my organic molecule, then I can't prioritize a bromo over a chloro or a chloro over a bromo, right? So when I have a situation like this, then I must give the lowest number possible to the most substituents, to most of the substituents. So I have 1, 2, 3 substituents. If I number from the right, yes, my first substituent is going to be bonded to the carbon, the second carbon. If I number from the left, also my first substituent is going to be bonded to the second carbon. But if I'm numbering from the right, it's going to be a substituent in the second carbon, then another one in the fourth, and then another one in the fifth, right? If I number from the left, my first one is going to be on the second carbon, then on the third, and then on the fifth. So when I look at the two, the numbering that is going to give me lowest number possible for most substituents is numbering from the left. Yes, numbering from the left. So I'm going to number from the left 1, 2, 3, 4, 5, 6. Right? I'm going to number from the left because I'm going to get lowest number possible for most of the substituents compared to numbering from the right. So I don't number from the bromo because it has a letter that comes first when I look at the alphabetical order. So now if I'm looking at it like this, so I'm just going to make a note here. Number to assign lowest position to most substituents, right? So now when I'm naming, I still have to consider writing in alphabetical order. So let's write down the name. It's going to be prefix, parent, suffix, and IUPAC name, right? My prefix is made up of my substituents. So I'm gonna have to start by naming the bromo first. I have to name in alphabetical order. So I'm gonna have to start by naming the bromo. So I have 5 bromo, right? I said there's a dash between a number and a letter. And then I'm gonna have 2.3 dichloro. So when I'm naming, the di that I add that indicates the fact that I have more than one chloro substituent, it does not factor in to my naming when it comes to the alphabetical order. My naming in alphabetical order is only based on the names of the substituents. right? And then the parent, my parent chain has 6 carbons. So it's going to be hex. And it has single bonds only between adjacent carbon atoms. So it's hexane. So when I put the name together, it's going to be 5 bromo 2.3 dichlorohexane, right? So here I said I'm going to number according to, in order for me to give the lowest number possible to most of the substituents. I can have another situation where I'm going to have to number in such a way that I prioritize the alphabetical order. So let's do it like this. If you look at this one, whether I number from the left or I number from the right, both substituents are going to be in the second position, right? So now this is the kind of question where I prioritize the alphabetical order. So I assign the lowest number to the substituent that starts with the letter of the alphabet that comes before the other substituent, right? So I have B coming before C, which means I'm going to give a lower position to the carbon that has the B, which is bromo, bonded to it. So it means I'm going to have to number from the right, right? And then my name is a prefix, a parent, and a suffix. And then when I put it together, I must have an IUPAC name, right? So I'm going to have my prefix is 2 bromo 3 chloro, and then my parent is but, my suffix is ane. I put it together, it's 2 bromo 3 chloro butane. Like I said, this is all going to be, there's only a dash between a number and a letter, right? So you can also have other kinds of substituents, which we call alkyl groups. You can have other kinds of substituents we call alkyl groups. We can have a methyl, ethyl, and propyl, and so on. But we usually deal with the methyl and ethyl as substituents. So it should be already ringing a bell in your head when you see meth. Yes, it's something you know. From that naming of the parent chain, meth means there's one carbon, right? So you can have a carbon or substituent which contains one carbon that is along the longest chain, bonded to one of the carbons in the longest chain of the organic molecule. You can also have a substituent which has 2 carbons along the longest chain, right, bonded to one of the carbons that are along the longest chain. So you can have a substituent that is a methyl. You can also have a substituent that is an ethyl. like that. And you can also have a propyl, which would have 3 carbons. Let's make an example here. Right? So if you're looking at this, I always say you have to identify the longest carbon chain. So the longest carbon chain has to literally be that, a chain, which means it can't break along the way. You can't break and then continue the chain from another position, which is not consistent with where you started numbering. So for instance, you can't say you have a carbon chain of 1, 2, 3, 4 carbons. It's no longer a chain because this one is just on the side. So a carbon chain has to be carbon bonded to another carbon, bonded to another carbon, bonded to another one. The longest one that you can get, that's going to be your parent chain. So when you look at this molecule, the longest carbon chain that you can get is 1, 2, 3 carbons, right? And then this one becomes a substituent. Another person could have numbered like this, 1, 2, 3. It's all the same, right? So then this becomes a substituent. So when I look now at my prefix, parent, and suffix, then this becomes my prefix. I have to check how many carbons are there in this side chain. This side chain, prefix, parent, and suffix. This side chain, if it has, like in this instance, it has 1 carbon, then it means I call it a methyl. And then I have to also indicate its position. So it's going to be in the second position, 2 methyl. And then I still have my longest carbon chain, 1, 2, 3, which is prop. And this is still an alkane, which is ane, right? So the IUPAC name will be 2 methyl propane. When it comes to substituents, I can have either just alkyl groups, which is methyl, ethyl. I can have halogens, which is bromo, chloro, fluoro, iodo, or I can have both in one organic molecule, right? So you have to know how to name all of those different scenarios. Let's look at an example here. More examples. We're just naming. Let's name this molecule. I hope you're just pausing the videos and trying all these out by yourself, which is usually more helpful than just watching. Right? So we can have an organic molecule where you have both bromo or halogen substituents and alkyl substituents, like in this instance. So what do you think I should do? Remember I said we can either have a situation where you prioritize giving the lowest number possible to most of the substituents. You can have another situation where you just prioritize alphabetical order. Which one do you think it is for this example? As you can see, if I start numbering from the right, then my substituent is going to be in position 2. Same thing if I number from the left, which means I have to number according to alphabetical order, right? So I'm going to have to start numbering from the right, because B comes before M. This is a bromo substituent. This is a methyl substituent. So I'm going to number 1, 2, 3, 4, 5, right? Then we go on to name. Prefix, parent, suffix. My prefix is going to be 2-bromo, 4-methyl. Parent is pent, and it's an alkane. So when I write down the full name, full IUPAC name, 2-bromo, 4-methyl, pentane. Right, these are just basics of the first 4 different kinds of functional groups that we can have. So today we just covered alkanes, alkenes, alkynes, and haloalkanes. I'll do another video where we're just practicing examples of naming, more examples of naming, and then I'll also do some past papers with that video, and then I'm going to continue with the naming of other organic molecules. Thank you for tuning into my YouTube channel. See you next time.